Perfect. So thank you very much for allowing me to talk today about this work that we have been doing within the Gravity Consortium to map the core of Eta Carina with near-infrared interferometric observations. So probably, as all of you know, massive stars are quite important for the chemical evolution of the galaxies. This is mainly because they exert a tremendous influence into their surroundings because they have huge mass loss rates, very strong stellar winds, and they also die in the form of supernova explosions. One example of these interesting interactions of the massive stars with the interstellar medium is Eta Carina. Perhaps this is the most astonishing and prototypical example. This target has had or has gone into several episodes of ejecta over the last 200 years that we have been able to map. And since the 1990s, there has been compelling evidence that indeed at the core of this star, or at the core of this target, is not one single very massive star, but a binary system. So there are some, here on the screen I plot and I put some of the properties of the binary solution. So basically Eta Car is moving, or the binary in Eta Car is moving in a very eccentric orbit with a period of the order of 5.5 years. We know that the massive star is very, very massive, I mean, with a stellar mass above 100 solar masses. And the properties of the secondary are not so well restricted. We know that there is a binary because of the indirect evidence that we have in their surroundings in the interstellar medium, but indeed we haven't been able to observe the binary directly. We haven't been able to resolve the binary directly with any kind of observations. In the case of the infrared interferometric observations, we haven't been able to do it yet. So this was the motivation to trying to understand how the interaction of the binary system in Eta Carina indeed repercutes over the interstellar medium around it. So for this, we use the Very Large Telescope Interferometer, which is these sets of telescopes that you have here on the screen. They can be combined to form an interferometer. Either you combine the fourth 8-meter telescope or the fourth 1.8-meter telescopes. So the maximum baseline, the maximum separation between a pair of telescopes is of the order of 130 meters, which at 2.2 microns in K-band, it translates into a resolution of 2 milliarseconds, more or less. So in interferometry, for those of you who are not familiar with the technique, we do not basically record directly the images of the sources. Instead, we record interference pattern produced by each pair of telescopes that we have in the interferometric array. And by sampling different patterns across different position angles in the sky, we can then retrieve some information about the brightness distribution of the object. Particularly, we can see if the object is resolved and how asymmetric it is. So we work with two observables, square visibilities and closure phases. And from these two observables, we indeed try to recover or reconstruct images of the source that we are observing. And this is indeed the work that we have been doing with gravity over the last 4 years. So the core of Eta Carina has been has been imaged with several techniques in the past. For example, here on the screen, I present you an N-band at 8 microns image obtained with the infrared camera Visier. And then you have 3 different reconstructed images obtained with interferometric observations with different instruments. So here, for example, you have an image reported by Weigel and collaborators in 2016 of bracket gamma obtained with amber in the K-band. Then you have this compact or continuum image obtained with Pioneer at 1.7 microns. And more recently this year, Weigel et al. Published again some images obtained cross bracket alpha in the L-band at 3.8 microns for the first time with Matisse, the new beam combiner at the VLTI. So this is, so we decided to use gravity to continue the mapping of the core of Eta Carina. So if you look at the previous images, you can see that indeed the core changes a lot depending on the wavelength that we observe, and particularly we observe it across one of the spectral features. So it's very interesting for us to see how, how this, how that morphology is within the binary scenario. So again, gravity is a very astonishing machine. It works in K-band between 1.9 and 2.4 microns. It has an angular resolution of 2 milliards, but it also allows us to disperse the light to have a spectral resolution up to 4,000. And this is important because it allows us to resolve some of the broad spectral features that we might see in the K-band spectrum, in this case of Eta Carina. So in 2016, we published our first reconstructed images using gravity. At that time, we only used one interferometric epoch obtained in 2016 during the commissioning time of the instrument. But now we added two complementary epochs to our study, one obtained in 2018 and the other one obtained in 2019. So what I show you here on the screen are this coverage of the UV plane that we got with our interferometric observations. And as you can see, it is very good for just having 4 telescopes. And then we can try to reconstruct images out of those data sets. Recovering images from infrared interferometric data or from interferometric data with sparse arrays is an ill-posed problem. I'm not going to enter into the details of the algorithms and so on, but we need to use a regularized minimization to recover the images. I just want to point it out that during the last year, there has been a lot of effort in the community to put out some softwares available for everyone in order to perform these reconstructions. Some examples of the softwares are Squeeze, VSMEM, Myra. In our case, we use the Squeeze, which is a software that was developed by Fabian Baron, reported in this paper in 2010. And what we do is that we image 35 different spectral channels across bracket gamma in the K-band to create a cube of very high resolution images of the core of Eta Carina. So here on the screen, you have some of the setup that we use for the reconstructions. For example, we have a field of view of 100 milliards, pixel scale of 0.6 milliards. But I think what is important from this table is the fact that we try to fit simultaneously all the observables that we got in the gravity data in order to recover simultaneously the cube of images across the line. So here you have, as example, one of the normalized spectrum of Eta Carina. So this is the spectrum in K-band obtained with gravity. You can recognize some lines here. For example, this is helium 1 line, magnesium 2, and then this, the most or the brightest one, or the brightest one is indeed bracket gamma. So if we do a zoom towards bracket gamma, you can see here the different spectral channels that we have across the line. And here you see the reconstructed images that we got, in this case with the 2016 data. So you see that we move from this very compact core that it was observed in the H-band data with Pioneer and as we move towards the center of the line, we observe that the structure is changing and it becomes more extended. And in some cases, we even see here a kind of shock front in the reconstructed images. Just as an example, I plot you here the square visibilities and here the closure phases. In gray, you have the data, and in colors, you will see how fit our reconstructed images reproduce the interferometric data. For those of you who have done this kind of work in the radio or radio wavelengths, you may think that this is very, I mean, this is not so astonishing, but for us in the near infrared, this is really the state-of-the-art reconstruction. And so we repeated this process for the other 2 epochs that we have in our data sets, and this allows us to map the changes that to map the core of Eta Carina.
2 minutes left.
This is very interesting because in the 2018 paper, we just suggested that there were some temporal variation of the core of Eta Carina, but we couldn't be able to resolve it properly or to make an image. And now with the 2 new data sets, we were able to reproduce these changes. In this slide, you see clearly 5 different spectral channels, some of them blue shifted and some red shifted for the 3 different orbital phases, and you clearly see that the structure of the target is changing with the orbital phases of the secondary. But how does this fit in the binary model or in the binary scenario? Well, you have here this very good simulation performed by Madura and collaborators in 2012 and 2013. And basically the idea is the following. We have a very massive star in the center with a very dense but slow stellar wind, and then we have the secondary orbiting around. The secondary star has a lighter wind, but it's much faster with a terminal velocity of around 3,000 kilometers per second, so that the secondary creates a cavity, a wing-wing collision cavity as it orbits around the primary. And we suspect that the material that we observe from the cavity, so the material that we observe in our bracket gamma images is indeed the material flowing out along the cavity walls of the cavity. And of course, depending on the position angle and the orientation, we see different structures because the cavity goes into this spiraling process as it approaches to the periastron. I don't have more time yet, so I will let you with my summary. So we present the first images of the time-evolving Eta Car of Eta Carina. The most extended emission is observed at low-shifted velocities, at least for the 3 epochs that we have. The extended structure in the images is consistent with this wing-wing collision scenario. We observe time-dependent changes at all spatial scales, and of course, we require future radiative transfer and hydrodynamic simulations to constrain the physical parameters of the observed structure in our images. Thank you very much.
Thank you. So, any questions about Eta Car, but this time something different, so the structures? Okay. I don't see anything yet. Ursula, yes, please.
It's just a quick question. Sorry, I think I dozed off a little bit, but it's almost 2 in the morning here, so I'm just getting a little tired. But what was the last simulation you showed? What was the code you used? What was it?
So these are the hydrodynamical simulations reported by Madura in 2012 and 2013. I just use this simulation just to explain more or less the physical scenario, but this is not something.
Okay. Thank you.
So the main idea of this work, I just wanted to point it out that this is a long-term monitoring program within the Gravity Consortium. And the main idea of this work is to basically monitor how this wing-wing collision cavity changes across the whole orbital period of the binary, with the idea of getting getting more information about how is the mass loss rate, or if the mass loss rate is constant or if it's changing across the orbital period, just to see how this can, for example, be, how the mass loss rate basically works as a precursor of one of these ejecta episodes that we have seen already on Eta Car. How the changes in the mass loss rate. That's what we really want to investigate with this work.
Okay, Ryosuke has a question.
Thank you. Yes, this was a very fantastic talk. Do you already see any like north-south differences in the shape of what you see? Because I was wondering if you can start constraining the inclination angle of the orbital plane with respect to the line of sight already.
Well, we see it here.
Yeah.
Here you see that at this orbital phase, very close to the apastron, you see these kind of shock fronts here. I don't know if you have seen these papers using HST images where there are some indications that there are some shells or kind of arcs that formed by shells over different orbital periods that are observed. We suspect that this is like the more inner shell that is produced at this time, but we haven't been able to confirm that yet.
Is this green? Oh,
sorry. You mean, Joel, that they were produced at apastron?
Nearby the apastron, yes.
Okay.
Indeed, we wanted, okay, so this was a little bit unfortunate because we really wanted to have images of the periastron passage last year. Unfortunately, we got some data, but it was not enough to make an image because parallel stop operations last year in April or something like that, which was more or less the time of our observations. But I didn't include those ones here because we didn't have images of those ones. But we want to do the parametric model fitting for those observations just to complement what we have with our images.
Okay.
And hopefully we will get a new epoch for this part of the orbit next year, early next year.
Okay, Ryosuke, anything else?
So I just wanted to ask you, is this green like orbit something that you constrain, or is it just like there to guide the eye?
No, that's the best fit orbit reported by Teodoro et al. In 2016.
That was by using the iron lines, wasn't it?
Mhm.
Yeah, okay.
Okay. So if there is no more question for Joël, I propose that we thank all the speakers. You can just unmute and clap a little, or just put clapping hands. Okay.